then even, for an unbounded value of t, I'm going to have a continuous dependence. Okay? So that's continuous dependence. Let's take a look at how solutions behave to the wave equation as we take t off to infinity. Okay? So, for example, okay, let's take the following version of the wave equation with a specific wave speed of 2. And let's take the initial conditions so that u of x is some phi, which we'll describe in more detail shortly, and the initial velocity is 0. Okay, and so x lives in r for these initial conditions, and then x lives in r and t is greater than 0 for the PDE. Okay, and let's take in particular for our IEC that we want phi to be a tent function. Okay, so I'm going to take a tent function that goes from 1 to 3. Okay, has a value of 1 at 2 here. Okay, and what we're going to see is how does that tent function propagate. So we already sort of looked at something like this in the case of the transport equation. What happens now in the case of the wave equation, where we know that any disturbances in the position of the medium is disrupted on some compact region. Okay, so the idea then is that the support of x is, the support of phi, okay, is just that open interval from 1 to 3. If you prefer, as we discussed before, you can make that a closed interval depending on your conventions. So here the support is just x such that phi of x is not equal to 0. Okay. And so oftentimes we may take the closure. Then we have x is in the closed interval of 1 to 3. Okay. So the solution to this PDE, we know by D'Alembert's formula, right? It's just u of x equals 1 over 2 of phi of x plus 2t plus phi of x minus 2t, okay? And so that's pretty straightforward. What we want to look at now is what happens to the solution to the solution u as we move forward in time. Okay. So the first thing I want to observe is that we have piecewise linearity of phi. Okay. And this means we have jumps in slope, okay, of u at x equals, x plus or minus 2t is equal to 1, x plus or minus 2t equals 2, x plus or minus 2t equals 3, okay? And just to illustrate that, let's draw our tent function, or just draw the region where a tent function is defined, right? So this is our x-axis. This is 1, 2, 3. This is our t-axis here. And we can see that these points, right, they're gonna propagate. And they're gonna propagate this way. And that's our, that's the bounds of our region of support. And I'll just put a dotted line here. And that's the propagation of the peak of our tent. And these are the edges, right? So in this region here, right, U is not equal to 0. Over here, U is not equal to 0. But in between, U equals 0, right? So our characteristics are these rays that propagate away from the initial condition. Here, if this is 0, we're crossing the t-axis here at t equals 1/2, right? This is our line x equals 2t, x plus 2t equals 1. Let me do that a little bit better. So this is the line x plus 2t equals 1, okay? This is the line x minus 2t equals 3, right? This is the line x minus 2t equals 1, and so on, right? So you can draw in all your representative characteristics, okay? And as we're saying here, right, only this region in between these prominent characteristics, okay? So only part of xt plane has non-zero u, okay, due to the compact support of u, okay, sorry, of phi of x, right? Moreover, you have 0 for your initial velocity, okay? So this is what happens now to your solution, right? It propagates left and right from your initial conditions, okay? And this brings up the notion of the domain of dependence of a particular point in your space. The idea with the domain of dependence is that you're looking at some point in the plane, and you want to know what's the region in your xt space that determines the value of your solution at that point in the wave equation, okay? Well, if you look backward in time, you know, maybe back to the point t equals 0 here, the region that matters is this box, right? Right here. That's your domain of dependence. Okay. So the idea here is that, you know, if we have a point here, we look backward this way and we look backward this way. Basically, the only thing that's going to determine how the solution behaves there is anything in that triangle, right? You know, depending on how far back you have to go to the initial condition or just to a previous value of your solution, okay? So the domain of dependence, okay, requires that you define the backward characteristics, and that's just what it sounds like. It's just the characteristics drawn backwards, okay, through x0 and t0, okay, where t0 is greater than 0, okay? And in particular, you want to propagate them all the way back to, let's say, your initial condition. So x plus ct equals x0 plus ct0. And that's defined for t goes from 0 up to t0, okay? So this should intersect the x-axis, right? At x is equal to x0 plus c t0, right? Because if we just plug in t equals 0 right there, right, then that just gives us this formula, and that tells us the bounds of this triangle that defines what is this region that's going to determine my solution at this point forward in time. Okay, so the solution at x0, t0, okay, only depends on the initial data on x0 plus minus c t0 up to c t0, okay? And this is sometimes what's called the interval of dependence, okay? It's the interval of my initial condition that determines a particular future point in time, okay? x0, t0, okay? The last thing I want to define, I'll advance the slide to do that, is what's called the region of influence, okay? And this is sort of the flip of the domain of dependence. This says, well, let's take x0, t0, okay? The region of influence is the set bounded by the forward characteristics, x plus ct is equal to x0 plus or minus c t0, for, in particular, for t greater than or equal to t, okay? And it just tells you, well, if I start at x0, t0, this is the region, let's say at time t, that's going to be influenced by this particular point, okay? So this would be x minus ct equals x0 plus ct0, okay? Or minus ct0, excuse me. All right, so, or, you know, maybe put more simply, x minus c t minus t0 is equal to x0. Okay, so if you take t to t0, then we get x equals x0, okay? So you may also talk about the region of influence of some interval from A to B. And that would be given by a trapezoid with you know, characteristics emanating out of the edges. And this whole region would be the region of influence of x is in A to B, basically at t equals 0. So here's your, well, t, let's say t0 equals 0, right? And then here's our later t, okay? So just two different perspectives of how a point is influenced by initial conditions that precede it, and also how the solution at a particular point is going to influence the solution at a future point in time. Okay, so so that's a couple of definitions. You'll probably